Hello everyone, I welcome you in my YouTube channel. I am Dr. Stereochemical. Today in this video, I will talk on group theory and symmetry. I hope this video will be helpful to you. If you like this video, then subscribe my channel. So friend, let us start group theory and symmetry. So look at this molecule. This is water molecule. There are two-fold rotational axis in water. So I will talk first about the molecular structure. The most powerful idea in chemistry is the idea of the three-dimensional structures of the molecule. Two techniques have been invaluable in this regard. One is NMR, nuclear magnetic resonance, and the other is X-ray crystallography. X-ray crystallography has been intensively developed as a technique which involves the ideas of symmetry of molecules. Understanding NMR also involves an understanding of symmetry. Group theory is also vital in understanding and predicting infrared and UV visible electronic spectra. On the next two slides are structures of complexes of metal ions determined by X-ray crystallography. These are shown simple to illustrate the power of X-ray crystallography in determining molecular structure. Determining such structures relies heavily on a knowledge of symmetry and group theory. So friends, crystals of CdPp2 Cl4 viewed through a microscope, you see 200 micrometer. So X-ray diffractometer, monochromatic X-ray source, example copper K alpha X-rays, X-ray source, single crystal on goniometer, detectors and computer analysis. This is the X-ray diffraction pattern. The actual structure of CdPp2 or 2+ complex cation. You can see here cadmium 2 cations and DPP ligands. So important of X-ray crystallography, NU or angle 63, oxo 2- anion and PDA ligands. The structure of UO2 PDA determined by X-ray crystallography. Now unit cell of UO2 PDA. Structures of proteins. FES cluster, sulfide, sulfur, cysteine sulfur. This is a structure of ferredoxin. Ferredoxin, Fe containing protein used for electron transport in bacteria. Now you can see here facial symmetry, and this is the importance of symmetry. You can see in first picture there is no symmetry. In the second picture this is the facial symmetry. Invariance to transformation as an indicator of facial symmetry. Mirror image. Now symmetry. Symmetry is very important aspect of chemistry, and an understanding of it is important in spectroscopy, crystallography and molecular orbital calculations. An example of this is seen in comparing the two molecules below, benzene and chloropenzene. We can all see at glance that A is more symmetrical than B, and that A will have only a single peak in the proton NMR, while B will have the 3 in more complicated situations, it may be more difficult to work out such things and an analysis of. So symmetry allows us to predict such things as spectra following mathematical rule. So symmetry is defined as invariance to transformations. What this means in simple terms is that if we perform a symmetry operation on a molecule, it should not appear to have changed. Thus, if we rotate a water molecule by 180 degrees about its two-fold axis of symmetry, it should not appear to have changed. So, rotate by 180 two-fold axis, molecule appear unchanged. So, transformation of the benzene molecule. The presence of a symmetry elements is identified by the fact that we can carry out a symmetry operation without molecule appearing to have changed. Thus, for benzene molecule, rotation by 60 degree about the six-fold rotation axis does not change its appearance. Rotation by 60 degree six-fold rotation axis. The rotation axis is a six-fold rotation axis because we can repeat the operation 6 times before we get back to the original orientation of the benzene molecule. So now the symmetry operation form a group, which is to say that any two of them carried out must have the same effect as one other operation in group, and one element of the group must be do nothing, that is the identity. The symmetry elements considered in group theory in relations to molecules are axis of symmetry or axis of rotation Cn, mirror plane sigma, center of symmetry I, improper rotations Sn, and identity total 5. The two most important symmetry elements, axis of rotation and mirror plane. One need to be able to identify the symmetry present in molecules are, you see, axis of rotation Cn. An object has axial symmetry when it is invariant to rotations by some fractions of 360 degree. It is said to have an n-fold axis of symmetry or a Cn axis when it is invariant to rotation by 360 degree by n. Conventionally, rotation is clockwise. Some examples of rotational symmetry are C3 or three-fold rotation axis of the ammonia molecules. If we rotate the ammonia molecules by 360 divided by 3 or 120 degree about this axis, its appearance is unchanged. Now rotation axis of BF3, principal axis, highest value of Cn. C3, three-fold axis view from the above, three-fold axis view from the side, two-fold axis view from the side, two-fold axis view from the above. So in BF3, C2 and C3 axis are present. So there are three C2 axis present in BF3 molecule. So what is mirror plane? Mirror symmetry means invariance to reflections, as shown for the molecular below. ZnI42 minus mirror plane CrCO4 6. So mirror plane sigma of BF3. Mirror planes can contain the principal axis sigma V or be at right angle to it sigma h. BF3 has one sigma h and three sigma V planes. So V for vertical and for horizontal. Look at here sigma V mirror plane. So C3 principal axis, sigma h mirror plane, C3 principal axis. So sigma V mirror plane contains the C3 axis, sigma h mirror plane is at right angles to the C2 axis. Now center of symmetry I. The inversions operation takes a point through the center of symmetry of molecule to an equal distance on the other side. Examples of molecules with a center of symmetry are center of symmetry dimethyl mercury, center of symmetry Cr0 hexacarbonate. For every atom as with the A atoms above, reflections through the center gives an identical atom vacuum. The center of symmetry is important in deciding whether orbitals are G or U. Improper rotation axis Sn. The improper rotation axis is invariant to rotation by 2 pi by n, followed by reflections through a plane at right angles to the rotation axis. This symmetry element is less important than the other and is necessary to create the complete globes. Most rotation axes that can be identified are also proper rotation axes. Example of improper rotation axis are shown here. Rotations by 330 60 degree by 4 S4. Reflection through the mirror plane at 90 degree to S4. So S4 improper rotation axis here is also a C2 axis. So S6 axis pyridine N oxide ligand. So rotational axis and mirror plane of the water. In water, principal axis is C2 and one mirror plane sigma V and another mirror plane sigma V. So water molecules has only one rotational axis, its C2 axis, which is also its principal axis. It has two mirror planes that contains principal axis, which are there for sigma V. It has no sigma H mirror plane and no center of symmetry. Now rotation axis and mirror plane of benzenes. Principal axis C6, C2, C6 sigma H, C2 sigma V, and principal axis and principal axis. So rotational axis mirror plane of boron trifluoride, principal axis C3, there is a sigma H. So boron trifluoride has a C3 principal axis and 3 C2 axis, a sigma H mirror plane, 3 sigma V mirror plane, but no center of inversion. So friends, hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.